Okay, so now we move on to the heart of kinematics, right? Physics uses calculus a lot, and it's worth understanding how calculus works because you're gonna need to use it in future in JC anyway. So, uh, differentiation. Okay, let's start off by talking about linear graphs, right? I'm sure you guys probably know how to find the gradient of linear graph, right? Y equals to mx plus c. Right? You take any 2 points. It doesn't matter which 2 points you choose because it's a linear graph. So any 2 points you pick will give you the same answer. But you take any 2 points and you consider as coordinates x0, y0, and x1, y1. Then you take these 4 values and plug it into the following expression, and you calculate a single real number. And that real number describes the slope of this function, right? How much the function increases or decreases, how much the function changed vertically as you move horizontally. Right? We sometimes call this rise over run. Yeah, and it's described by a single real number. So the question right now we want to ask is, how does this gradient of a linear graph, right? Linear meaning straight. How does this gradient of linear graph generalize to a notion of a gradient of a curved graph, right? So for example, I could have a function y equals to x squared, right? This is a curved graph we have plotted on the y-axis. So I want to have a notion of gradient of a curve, or more generally, curve means non-linear. Non-linear would be more accurate. I want to describe the gradient of a non-linear graph. And it turns out a natural way to define the gradient of a non-linear graph is to draw a tangent line. So keep in mind that this graph is non-linear, meaning that if I try to do the previous procedure on it by picking 2 points, right, it'll be problematic because the 2 points that I pick on the graph, right, I mean, they can give me different results if I choose different values. So if I pick another 2 points, it can give me different results for the gradient. So the previous notion of gradient completely doesn't work for curved graphs. And so the generalized notion of gradient is to draw a tangent line. So here's the procedure for calculating the gradient of a nonlinear graph. First we draw the graph, right? Then for each x value, so for example for this x equals to 2, right, value, for each x value, I want to go vertically up and find the point on the graph. The point on the graph is, in this case, x naught, right? So in this case it's 2, and 2 squared is 4. So the point on the graph is this. Then I'm going to draw a tangent line to the point, to the graph, tangent line to the graph at that point. So the tangent line is going to look like that. And this tangent line is a straight line, so I can take the gradient, right? And if we draw it super accurately, right, actually in reality we actually do calculations to figure out the gradient, but what you're going to get is that the gradient at this point is 4. Okay, and basically what we say is that the derivative of this function at this point, right, is 4. But I'll talk more about derivative soon. But for now, I want to talk about what if you plug in a different point. What if, let's say, you plug in x equals to -1. Let's say you plug in x equals to -1, right? I chose x equals to -1. That gives me the point -1, 1. And if I draw the tangent line to that point, I'm going to get a gradient. The gradient of the tangent line turns out is -2. And so calculus is the art of finding how to calculate these gradient values, right? How to, if I give you the function boxed in yellow, how can you give me the gradients of this function? yeah, and there's a very systematic procedure to do this, known as taking the derivative or differentiation. And yeah, so for now, before we go on to differentiation, I just want to emphasize that if we look at the linear graph, the linear graph's gradient can be described by a single real number, right? Single real number. The gradient is a single real number. In this case, m, right? And whatever 2 points we pick on the linear graph is going to give me the same real number, the same gradient. However, if I look at the non-linear graph, right, every single x value that I pick gives me a different tangent line, and a different tangent line will give me a different gradient. So in other words, right, we kind of need, because there's infinitely many x values, right, infinitely many real x values, I kind of need infinitely many real numbers to describe the full set of gradients at every point on the graph. So in other words, right, the gradient for a non-linear graph is infinitely many numbers, but there's a simple way to encapsulate this notion, and the easiest way is to encapsulate it in a function. And this function is gonna eat x value, right? And it's gonna output the gradient at that x value. And this function, it turns out, we're gonna call it y prime of x. So if the function I give you is y of x, right, then the gradient of this function is y prime of x, and that's what we're gonna learn to calculate next.